Hello, everyone. My name is Kevin Lance, and I'm the Director of Analytics Marketing at Unchained Labs. I'll be your moderator today, and thank you for joining us. We'll have a Q&A session at the end of the presentation. So to ask questions, all you have to do is to click on the Q&A button in the Zoom navigation bar at the top or bottom of your screen and type in your question. When submitting your question, please avoid clicking the anonymous button so we can reach out via email if we weren't able to get to your question during this presentation. And we will get to as many of them as we can. And now I'd like to introduce Andre Muller, Product Manager for Uncle at Unchained Labs. Today, Andre will walk through how to use Uncle as a one-stop stability tool to screen for the most stable proteins and most stabilizing formulations. He'll show fluorescence and light scattering data gathered on Uncle and use these to compare a few formulation conditions and their effect on protein stability. And now I'll hand it over to Andre. Andre, how are you doing?
Oh, I am doing very well. Thanks, Kevin. And I'm unmuted too. So let me start sharing the presentation. Thank you all for joining the webinar today. I will talk to you for the next couple of minutes about how to build up your formulation toolbox with Uncle. When you think of analytical lab equipment, most of it does one thing really well, and maybe there's a second function to it. When I think of Uncle, I would compare it more to this multi-tool. It is a collection of features that help you tackle most of your issues that you might have with biologics and biologics formulation, and is a true multi-tool, a one-stop shop for all your protein formulation and protein stability needs. How does Uncle do this? Well, Uncle combines several different modalities of measurement. We have fluorescence, we have static light scattering, and we also have dynamic light scattering in a temperature-controlled environment. In terms of the fluorescence, we measure full spectrum fluorescence between 250 and 720 nanometers, and we excite this fluorescence using a UV laser at 266 nanometers and a blue laser at 473 nanometers. Those two lasers are also used for the static light scattering measurement. So we are able to record the static light scattering as a readout of aggregation at two wavelengths, 266 nanometers and 473. A third modality, DLS, is also giving you information about the aggregation state. So I have an orthogonal technique in addition to the SLS. I personally like using my DLS as a quick checkup before starting an experiment to make sure that my sample is still monomeric and there's no aggregates. If I'm working with an IgG type molecule, for example, I would want to see a diameter of around about 10, 11 nanometers and not see anything of 100 or 250 nanometers, which would indicate to me that aggregation has already happened and I better re-prep something before wasting time doing an experiment with aggregates. Uncle is temperature controlled. You can set the temperature between 15 and 95 degrees Celsius. That allows you to do temperature ramps, isothermal incubations over hours, days, weeks, and also you can set it to room temperature in case you want to do that DLS experiment I just mentioned. So Uncle packs these things together in one instrument and combines the modalities to a dozen different applications. Today, because the topic of the presentation is formulation, we will talk about here's the pointer, the TM Tagg application. We'll talk about the TM with Cipro, a DSF application. We'll talk about the isothermal stability, and we'll talk about the colloidal stability measurements, KD, B22, and G22. You can also use your Uncle for viral capsid stability, which is something I can't talk about today because we're talking about protein formulation, but just want to sow that seed. The heart of Uncle is the Unde. The Unde is a black anodized aluminum frame with 16 9 microliter quartz cuvettes in it. Each of these cuvettes will take your sample. You can load it with a single channel pipetter, or you can use it load it with a multi-channel pipetter. It's really easy to load. And then you insert that Unde into the blue Unde frame that has silicone seals at the top and the bottom of the cuvette and seals it off, so you don't have to worry about evaporation. In a temperature ramp, in an isothermal experiment, or even if you go through a freeze-thaw cycle, the silicone seals seal the cuvettes off and you don't have to worry about any loss of sample. And this is a good holder for the sample in the measurement, but also for incubation outside of Unde or in a freeze-thaw cycle. Once your sample is loaded into the uni, you insert the uni into the instrument like this. Door opens, the tray slides out. You take the lid off the tray. That shows you the Peltier heating element. You place your uni on that Peltier heating element, replace the lid, the tray slides back in, the door closes, and the instrument is ready for the experiment. There's no other hardware interactions other than loading the uni and loading the uni into the Unde. As you could see, there are 3 spaces for the unis. That means you can put between 1 and 48 samples into one experiment. If you're doing a fluorescence measurement with Unde, the raw data looks something like this. So here in this case, we see the full spectrum fluorescence that was recorded in Unde between 250 and 720 nanometers. And we have one fluorescence emission curve per temperature increment. So every degree, we're reading the fluorescence. And these fluorescence reads with progressing temperature are showing lower and lower intensity. They also, if you look at where the maximum is placed, it shifts a little bit to the longer wavelengths. It shows a typical redshift. So why does the fluorescence decrease and shift to the red when we are melting our protein in a temperature gradient? That is because the aromatic amino acid residues that are in charge or are responsible for the fluorescence, they are usually on the inside of the protein in a hydrophobic environment. And as the protein melts, they become more mobile, they are turned to the outside, they find themselves in a hydrophilic environment, which changes their fluorescence cross-section, their fluorescence, and the fluorescence intensity as well. So that's why in increasing degrees of melting, we observe a change of the fluorescence, lower fluorescence, and also a shift towards the red wavelengths. What I want to point out here is this spike here, which is our static light scattering spike. So this is at 266 nanometers, and it's red at 90 degrees. And if we quantify the area under this peak, we can use this information for our static light scattering and to find out about potential aggregation of our sample. This is a good segue and leads into the next slide. If you are using Unde's Tagg application, it's really a 2-for-1 application. You read out 2 important factors about your sample in one go. Let's take a look at it in detail. I have the fluorescence on the left y-axis here and in blue, and we have the static light scattering at 266 nanometers on the right y-axis in green. We're going on a temperature gradient from 25 degrees Celsius all the way to 90 degrees. So if we follow the fluorescence readout, we see the value increasing, and then there are two apparent melting points at the inflection points. The software does this by determining the first derivative and then calling the melting temperatures 1 and melting temperature 2. What I want to point out here is that we are displaying the BCM, the barycentric mean, which is the center of mass, the spectral center of mass, if you want. It's the wavelengths which divides the area under the curve half to the left, half to the right. So because we are reading full spectrum fluorescence with Unde, we want to really use that full spectrum fluorescence also in the evaluation. And the BCM allows us to integrate the entirety of the spectrum and lead to a high signal, low noise measurement this way. At the same time as we're reading our fluorescence, we're also reading our static light scattering. You can see that there is pretty flat signal until about 80 degrees when it starts spiking. Because static light scattering is a readout of molar mass, we can say that this is the point where aggregation happens, and we define a Tagg. In this specific case, the Tagg happens in concert with the second melting temperature. So TM2 and Tagg in concert. The nice thing about Unde is that you read these 2 things at the same time with the same sample in the same gradient. And so you have like the direct relationship between those 2 data sets, or these 2 reads of the same sample give you a good basis for analysis. So what can we do in case we have a buffer that wipes out our signal? In this case, we're looking at 3 different buffers, and we have protein in all 3 of them, the same protein and the same amount of protein. It doesn't look like it, but believe me that it's there. It's just that in buffer 2, one of the excipients quenches the fluorescence. in buffer 1, we see the normal progression of fluorescence. It decreases with increasing temperature, but buffer 2, we see nothing. In buffer 3, we have a decrease in fluorescence. It's not quite as bad as in buffer 2, but it's still not very good. Is there anything we can do? Is there anything Uncle can do to help us evaluate an experiment like this? Of course, Uncle to the rescue. Since we have the capability of reading out full spectrum fluorescence, and we use 2 different lasers to excite this fluorescence, we can use external dyes. So in this case, we can add Cipro orange to our sample and excite it with a blue laser at 473 nanometers, and then take a look at the readout from this Cipro orange to tell us about our unfolding of the protein, basically do a DSF experiment. What does this look like? Well, on the left side, just for comparison, I have the intrinsic fluorescence data. So for our monoclonal antibody in buffer 1, that was the one that does not quench fluorescence, we see the normal progression and we see 2 inflection points calling 2 melting temperatures. For the same monoclonal antibody in buffer 2, we see an increase, we see a redshift in the BCM values, but there's no inflection point. So there's no way, it's pretty noisy, and there's no way we can tell where the apparent melting temperatures are. If we add the external dye to it, however, we can call 2 melting temperatures in buffer 1, and we can also call 2 melting temperatures in buffer 2. What we can further deduce from this result is that the excipient in buffer 2 that quenched the fluorescence not only quenched the fluorescence, it also destabilized the protein, because TM1 and TM2 have shifted to lower temperatures compared to buffer 1. This flexibility of Uncle of using an external dye like Cipro orange is also the reason why we can easily use it for proteins that do not have any aromatic residues. So in case you have no intrinsic protein fluorescence, which is the case here, we have static light scattering signal at 266 and also at 473. We add our external dye, and then we get a signal that we can work with, and we can find out about the melting properties of this aromatic amino acid free protein. In sum, Uncle always sees what's happening. The fact that we are measuring full spectrum fluorescence and we have the flexibility of 2 lasers, we can focus on protein fluorescence, we can focus on dye fluorescence, we can also look at both and see if that gives us any added information. As I mentioned earlier, Uncle also uses DLS. So I'm going to give a brief introduction into a DLS measurement. DLS, dynamic light scattering, gives you access to the hydrodynamic diameter of a sample and also its polydispersity index. Here in this example, we have 3 different plots. In blue on the left, we have a low Z average diameter, low polydispersity sample. In the middle, we have increase in polydispersity index, slight increase in Z average diameter compared with blue. And in yellow, we have the biggest polydispersity index and the highest Z average diameter. These are not 3 independent samples. It's the same sample and a temperature gradient. So we go from 20 degrees Celsius to 70 degrees. This one was recorded in the center. So you can see that as the protein is facing increasing temperatures and it starts aggregating, we see the polydispersity index going up and also the Z average diameter. When we compare static light scattering and dynamic light scattering as a readout for aggregation, it would look something like this. So we have a solution of a IgG in PBS, 4 milligrams per milliliter, and we're looking at the Z average diameter from DLS in green, and we're looking at the static light scattering intensity in blue. As you can tell, both of these techniques, SLS and DLS, both pick up on aggregation. The signals increase in both cases. However, static light scattering reacts first. Both of these techniques are very sensitive towards aggregation, but the resolution of static light scattering is higher. So our preferred way of looking at aggregation is static light scattering. Of course, confirming that with DLS is always nice. So now that I have introduced the different modalities of measurement in Uncle, let's take a look at a screen for bad buffer behavior, like an A/B's test for 2 buffers. We have a monoclonal antibody. And we have it in its commercial formulation, which is a histidine formulation. And we buffer exchange it into acetate. I want to compare the melting and the aggregation behavior in these two systems. Histidine is in green, acetate is in purple, and you can tell that in histidine we see the normal progression of 2 inflection points, so 2 melting temperatures. Looking at acetate, these melting temperatures have both shifted to lower temperatures. They shifted to the left, so the acetate buffer obviously destabilized the protein. Looking at the static light scattering signal, in the case of acetate, we see at around 70 degrees a pretty sudden and pretty extreme increase in the static light scattering signal. So this protein as well, in concert with TM2 with a second melting temperature, starts aggregating, and in acetate it's aggregating pretty much. If you zoomed into the static light scattering signal from the histidine buffer down here, you would also see an increase, but it's not anywhere as close as anywhere close to the dramatic increase we see in the case of the acetate here. This being a simple 2-buffer comparison. If we're going into it a little bit more analytically and do a test of different excipients, this is what we're going to be talking about for the rest of the presentation. So we have our monoclonal antibody in its histidine formulation, and we added either sodium chloride or arginine or sucrose to it to test the effects of these excipients on the stability of the monoclonal antibody. I'm going to be using the same colors in the next couple of slides. So everything that is green is histidine, everything that's gray is the histidine with sodium chloride, yellow is the arginine addition to histidine, and in blue, sucrose. If we're first looking at the melting temperatures, we can see that the TM1 is shifted to lower temperatures in the sodium chloride condition and also in the arginine condition. Looking at TM2, the melting temperatures are much closer together. You could maybe say arginine is a little bit lower than the other 3, but it's nowhere near the several degree change that we see for TM1. We're looking at aggregation. We can see that while histidine and sucrose conditions remain pretty flat, there's a little bit of aggregation, but not too much. In the arginine and the sodium chloride condition, we see a pretty steep increase of the static light scattering signal, indicating that there is intense aggregation going on. This aggregation, all the aggregation events still seem to happen in concert with the second melting temperature, which is an interesting observation. We do in Unde also record static light scattering from the 473 nanometer laser. And because that has so far not been the star of the show, hasn't had its time in the limelight, I wanted to add this one experiment here to show static light scattering recorded with the 473 nanometer blue laser. This is an isothermal experiment. So we incubated our protein in the 4 different conditions for 19 hours at 60 degrees Celsius. 60 degrees were chosen because that's 5 degrees below the highest unfolding onset. And comparing the behavior of our protein in the 4 formulations in these conditions, you see that for histidine and sucrose, the line remains rather flat. So there's not much aggregation going on. In contrast, arginine shows aggregation and sodium chloride shows an earlier onset of aggregation, and also the aggregation progresses to a much higher level. So what we can tell here is that our protein seems to be okay in histidine buffer or in histidine with sucrose for 19 hours at 60 degrees, which is pretty rough conditions if you think about it. So that's an interesting result. To talk about colloidal stability and talk about another application that Unde brings to the table, I want to talk about B22, the second virial coefficient, and the KD, the diffusion interaction parameter first. In order to measure B22 and KD, we would take a room temperature snapshot of a concentration series. For an IgG type molecule, that concentration series would be somewhere between 1 milligram per milliliter and 10 milligrams per milliliter. As we are increasing the concentration of our analyte, the likelihood of interactions between the proteins increases. And these interactions can be one of 3. And this kind of traffic light model, I want to use this traffic light model to illustrate this. If the proteins are interacting attractively, they will be bigger, they will appear to be bigger than they actually are, which will lead to a decrease in the translational diffusion coefficient. The change of the translational diffusion coefficient is expressed by the diffusion interaction parameter, and for this case of attraction, the KD would be negative. If the interactions between the protein, the self-interaction between the protein is repulsive, they're going to be appearing to be smaller than they actually are, which means that the translational diffusion coefficient is going to be higher, which is expressed by a positive KD. So positive KD indicates weak repulsion of the sample, which means that for a formula in a formulation study, this would be beneficial because, of course, we want to formulate something in a way that it remains in the shell in solution on the shell for a long time and does not aggregate and doesn't precipitate. The B22, the second virial coefficient, would not be determined in a DLS experiment. This would be determined in a static light scattering experiment. But you can see that this Kc divided by R90, the Rayleigh ratio at 90 degrees, could also be plotted here. And the readout is kind of comparable. So also a positive B22 indicates weak repulsion, and a negative B22 indicates attraction. Now, let's take a look at our 4 formulation conditions from earlier. And we can tell that histidine and sucrose, which prevented aggregation in the isothermal experiment and also in the temperature ramp, have quite positive KD values. Arginine is neutral, and sodium chloride has a negative KD, which agrees with what we saw, the increased aggregation in this condition. Comparing the KD with the B22, they agree in these cases. That's not always the case. Sometimes there's a difference between the B22 readout and the KD, which is very interesting because it can give you information about the system you're looking at, but in this case, they agree. I mentioned that the B22 value is determined in a concentration series between 1 and 10 milligrams per milliliter. The G22, the Kirkwood-Buff integral, is something that is applicable to higher protein concentrations, so 50 milligrams per milliliter up to 100 milligrams per milliliter and beyond. Here, we're also measuring the static light scattering readout and doing this in a concentration series. And then if the G22 we determine is positive, it indicates attractive interaction. And if we are measuring a negative G22, it indicates repulsive interaction. The prefixes here are different the other way around compared with B22. Now, when we look at our 4 formulation conditions, we can see that the histidine and the sucrose condition have slightly negative G22 values. Nice, great. Arginine is more negative, and to our surprise, we found that sodium chloride is even more negative. So that means that in the high concentration of protein, the sodium chloride is actually beneficial in preventing aggregation, whereas in the low concentrations, histidine and sucrose were the better ones. So what do we do with this information? What would we do if we were doing this for a living? Well, I mean, first of all, we should review the data that we have, and then it depends a little bit on what the end game is, what we want, where we want to go with this. Do we want to formulate a protein for low concentration applications like ELISA, or is our aim really to have a high concentration protein formulation for injection? For the low concentrations, KD and B22 measurements showed us that histidine or the addition of sucrose are beneficial. For high concentration, the G22 measurement showed us that sodium chloride really could be our knight in shining armor preventing aggregation of the protein. With this information from this rather simple 4 excipient screen, we could design the next experiment and further refine our conditions and test how we can increase stability of our protein. With this, I'm at the end of the presentation, and I was able to go through some stories and formulation studies and show you how Unde can help you screen buffers in an A/B screen or help you screen for different excipients. In this example, it was 4 different ones. In the introduction, we talked a little bit about how you can use Unde to screen the stability of proteins, either with dyes or without dyes using the intrinsic fluorescence. And again, I want to point out, Unde is also going to be your friend and helper looking at the stability of viral vectors. If you need more information about that, let me know. Happy to provide that And with that, I'm going to go back to Kevin and ask him if there were any questions in the box.
Yes, Andre, there have been lots. People have been pretty active, so I'm excited to go through some of these questions and
Awesome.
talk a little bit about them with you. So thanks again for the presentation covering everything on Uncle from full spectrum fluorescence to static light scattering to even a look at some of the applications on dynamic light scattering that can be accomplished there. And really kind of the overall message was talking about using those different technologies and applications to distinguish stability and aggregation in different formulations. So, all right, for those of you that have already submitted a question, thank you. For those of you that have an idea, you can go submit a question in the Q&A button at the top or bottom of your Zoom navigation bar, and we'll tackle as many as we can. All right, so Andre, does the Uncle measure fluorescence and SLS at the same time, or is it one after the other?
Thanks for that question. The measurement of fluorescence and static light scattering happens at the same time. So Uncle has two optical systems. One is the DLS system, and one is the SLS and fluorescence system. So we're measuring static light scattering and fluorescence at the actual same time.
And then can you explain a little bit more about the Cypro orange application? There's a question if the Cypro dye is attached covalently to the protein or how that works.
Yeah, so if you do the protein stability measurement using Cypro orange, there's no covalent attachment of the dye to the protein. You mix the dye that you can buy from, I don't know, molecular devices or whoever provides it. You make a stock solution, you add that to your protein solution, then you pipette that mixture into the uni, put it into Uncle and go through the temperature ramp. When the protein unfolds and presents hydrophobic residues that are previously hidden on the inside of the protein, the Cypro orange will bind to those, and that interaction will cause the fluorescence of the dye to change. So it is a hydrophobic interaction between the dye and the protein. It's not a covalent binding. The fluorescence curve looks a little bit different for Cypro orange than it does for intrinsic fluorescence, but the principle is the same. We're looking at the presentation of hydrophobic residues, and we can exploit that with a dye that interacts with these and then change its fluorescence.
Yeah, it's actually almost one of the early examples of a thermal shift assay to kind of that sort of interaction where there's a binding event and then some sort of response. Can the Uncle sample holder be used for long-term isothermal studies? Are there any evaporation concerns or any chemical compatibility issues?
The Uncle quartz cuvette is made of quartz. The silicone gaskets are silicone, so as long as your material is compatible with quartz and silicone, you're good to go. Closing the frame and clipping it in place requires a little bit of force, so the seal between the quartz cuvette and the silicone is really tight, and there's no issues with evaporation. So isothermal experiments up to a week, temperature ramps, freeze thaw experiments, that can all be done. And as long as your sample, or as long as whatever is in your sample is compatible with quartz and with silicone, you should be good to go. And no worries about evaporation.
And then there were two, I think one came in possibly through the chat. Oh, I can look at it again. It's, can you define the range for the low and high concentration for protein typically around an Uncle?
The lowest end of the protein is probably in the range of 0.1 milligrams per milliliter, depending, of course, a little bit on the size of the protein. Maybe for an IgG, you can go as low as 0.05 milligrams per milliliter. When it comes to the upper end, I think, I mean, whatever concentration people normally are using, going up to 150, 200, maybe even 250 milligrams per milliliter should work. The optical system in Uncle has physical filters in it. So if you're going to very high protein concentrations, you might be concerned with saturating your detectors, but you can counteract that using the physical filters. As long as you as the experimenter can pipette your protein solution into the uni, you should be good to go. So I would say for an IgG, let's say between 0.05 milligrams per milliliter and 200 milligrams per milliliter, you should be good to go.
Actually, it's a good opportunity to refer back to our website because I know there's a webinar from about a year or so ago, looking specifically at high concentration proteins. So it's another good example of looking at what happens to fluorescence signal when you're way up in the 100, 200, 300 milligram per mil. So this is a question. Can the Unde be used for ICD experiments, which I'm going to assume means isothermal chemical denaturation or delta G experiments?
Yes, it can. There is an application. You might have spotted it earlier when I had the list of the 12 plus applications, and there's one for delta G. So in this case, you would have to pipette, or you would have to manually mix your sample with the increasing amounts of urea or guanidinium or whatever your denaturant of choice is. You tell the software what the concentrations are, and then it will use the fluorescence readout to determine the folded, unfolded ratio and give you the delta G information.
Okay. This question I noticed popped up during the KD B22 section. So how is the translational diffusion coefficient measured for that experiment? And then it's asking if it's fluorescence anisotropy or Stokes law of diffusion.
So when we do the KD measurement, we have a concentration series in a series of 16 cuvettes in one uni, and then we measure the dynamic light scattering of that. And then the diffusion interaction parameter KD expresses the relationship between the diffusion at 0 concentration, so extremely dilute, and the actual concentration. So it's a proportionality factor. So we are looking at the DLS, or we're using the DLS measurement to determine the translational diffusion coefficient as a function of concentration, and then evaluate that. The proportionality factor is the diffusion interaction parameter KD.
Okay, and that actually segues nicely to the next question. Do you need a standard, like a toluene standard, for the SLS experiment, the B22 experiment? And then eventually, I'll just read the question. Do you need a standard such as toluene for the SLS experiment to determine B22 and the apparent molecular weight?
No, you don't. There's no need to calibrate the system. We're not measuring absolute molar masses. We're measuring changes in molar mass. And for that, we wouldn't need a calibration. So toluene calibration of the uni is not necessary. Toluene calibration of the uni can be done, but we don't need it for the B22 measurement. We just need a concentration series of our analyte. Yeah,
and then for people that need to calibrate besides with toluene, we do have a aqueous-based calibration standard that's available, and it's the kind of thing where you do something like monthly, that sort of thing, but Unde will save the calibration, so it's not needed for every single run. Can the uni be reused for new applications?
Thanks for that question. The uni is designed for single use. So you use the blue frame is reusable, of course. We provide silicon gaskets with the unis. So you load your uni, you use your uni, and then you replace uni and the silicon gaskets. Think about what you do with a uni. You go through a temperature ramp and you're basically denaturing protein, which will then be stuck to the sides of your quartz cuvette. Would you want to reuse that? Can you make sure that you can clean it and use it again? They are designed for single use, and that's the way they should be used.
Okay. So,
maybe I can say one thing. If you have a uni and you use only one well, of course, the other 15 you can use later. There's no problem with taking the uni out, loading another well later. So it's not like you can only, if you have only one sample, you're wasting a full 16 uni set. That's not the case. But once an experiment has run in one well, that's going to be used.
Okay. And there's a question about the first fluorescence spectra. So, early on in the slide deck, there were spikes in the fluorescence spectra. What were those?
The spikes, are you talking about the one? I'm assuming that the question is about the spikes that you see next to the intrinsic fluorescence. There's one spike at 266, which is the 90-degree angle static light scattering that we use to determine that. Then when we use the 473 nanometer laser, we have a spike there as well. That is the signal that we use to quantify light scattering at 473. And then sometimes you see some effects at the multiples of the wavelength. So 266 times 2 is 512, 522. 532. 532. There's a spike there as well, and there's also one at the multiples of 473. So those are effects of the measurement of the laser, and they're not something that's intrinsic in the sample. This is something that's due to the hardware setup.
Okay. Can you do isothermal DLS in addition to fluorescence and SLS that you showed?
Yes. So the isothermal experiment I showed, the 19-hour experiment, I only showed the SLS at 473 nanometers. We can also, of course, record the SLS at 266 there. We can record fluorescence there, and we can also record DLS. Not a problem.
Okay. And I think we'll do one more question since we're 5 minutes sort of over time here. So can this instrument be used in a 21 CFR part 11 environment?
Yes, it can. We have a software flavor that is GMP compliant, and we can also provide qualification of the instrument. So installation qualification, operational qualification, and then audit trail in a 21 CFR Part 11 compliant flavor of the software, if you want to call it that. No problem.
Yeah, so there are a few more questions that we're not able to get to, but I noticed I kind of reserved those questions since we're able to see your names, and we'll follow up with you so you make sure to get your answer that you need. So thanks to our audience for answering all of those, or for asking all those great questions, and thanks to Andre for answering them. And thanks to everyone for joining us. If you want to have a deeper conversation with our team, please do get in touch with us at info@unchainedlabs.com, or you can learn more at our website at unchainedlabs.com. I would love to connect with you. Thank you again for attending our virtual seminar, and I hope you have a great rest of your day.
Thank you very much.